In this video, we're going to talk about the product and quotient rules. Our objectives will be to answer conceptual questions involving the product and quotient rules, to find derivatives of products and quotients using algebraic expressions, to find derivatives of products and quotients of functions involving exponentials, and to find derivatives using the extended power rule. So we're going to actually have to talk about the chain rule a little bit in this video, even though that's really our next topic that we're going to talk about. So first things first, let's tell you what the product rule and the quotient rule are not. It's not that the derivative of the product is the product of the derivatives. Do not do this. This is wrong. Also, the derivative of a quotient is not the quotient of the derivatives like this. Don't do that. That's wrong. That's why I'm writing it in red. So this is why we have the product rule to take care of products and the quotient rule to take care of quotients. Follow these rules, memorize them. They are very important. So our product rule, if f and g are differentiable functions of x, then the derivative of f of x times g of x is equal to f prime of x times g of x plus g prime of x times f of x. I can write this with a bunch of colors, but I'm going to use the space instead. Let's go ahead and do this. If I have f of x times g of x like this, then that's going to be equal to, I'll make this f prime of x times g of x plus. Hopefully this helps you and doesn't make your eyes go crazy. G prime of x times f of x. Now I prefer to do this with the u's and v's, and you'll see why when we do the chain rule later. So I like to write the derivative with respect to x of u times v is equal to u prime v plus v prime u, like that. Okay, so that's what you're going to see me writing, where u is the first function and v is the second function. And the reason that I do that is sometimes we call the product f of x or g of x, so I don't want to use f or g as my variables inside the product rule. I want to use dummy variables to replace them, u and v. So in this case, evaluate the following using the product rule. So we can actually use the power rule here. We don't need the product rule, but if we used the product rule, we could do something like this is the derivative with respect to x of x times x to the third. And then we would take the derivative of the first piece, leaving the second piece alone, plus the derivative of the second piece, leaving the first piece alone. And then we would get x cubed plus 3x cubed is 4x cubed, but we already knew that should have been 4x cubed by the power rule. Our power rule told us that we should get 4 times x to the 4 minus 1 is 4x to the third. So that checks. All right, let's go ahead here and take the derivative of this first piece, leaving the second piece alone, plus derivative of the second piece, leaving the first piece alone. Derivative of the first piece here is 2x. Then leave the e to the x. The derivative of e to the x is e to the x times x squared. So this is x squared plus 2x times e to the x, or e to the x times x squared plus 2x. If you prefer, you can leave it all factored out or all expanded out, but I like to factor my answers. You'll see why later on, because usually we're interested in where these derivatives are equal to 0. So it's easier to answer that question once they are in factored form. All right, so we have a couple options on this one. We could expand it and use the power rule. Let's see what that would look like if we did that. So it turned into 3x cubed plus 3x squared is going to be 3 times 3 is 9, plus 2 times 3 is 6x. So let's check and see if we can get that with the product rule. So we want derivative of the first part, leaving the second part alone, plus derivative of the second part, leaving the first part alone. 6x squared plus 6x plus 3x squared is 9x squared plus 6x. In both cases, I'd probably want to pull out the 3x as a common factor and leave this with 3x plus 2 and 3x times 3x plus 2. All right. Let's look at the quotient rule now. If f and g are differentiable functions of x and g of x is not equal to 0, then the derivative of f divided by g at x exists and is, let's write f of x and g of x with the colors again here. And we want g of x in these two spots here. And then this is going to be f prime of x here. And f of x g prime of x. All right, so the way that I write this here is the derivative with respect to x of u divided by v is u prime v minus v prime u all over v squared. And that looks a whole lot like the product rule that I wrote earlier. See, this was u prime v plus v prime u. So I just change that to a minus and divide it by the v squared. And I have my quotient rule. And that way I'm not writing these in a different order here. So let's evaluate the derivatives here using the quotient rule. Let me just go ahead and set up my table here. U is my numerator. V is my denominator. So u prime, the derivative of u is going to be 2x. And v prime, the derivative of v is going to be 2x. So I want u prime v minus v prime u all over v squared. And then let's factor. So we have 2x as a common factor, x squared minus 1 minus x squared plus 1, like that. And this is over x squared minus 1 quantity squared is 2x times x squared minus 1 minus x squared minus 1 over x squared minus 1 quantity squared. X squared minus x squared is 0. 2x times a negative 2 over x squared minus 1 quantity squared is a negative 4 over x squared minus 1 quantity squared. For x, 2x times a negative 2 is a negative 4x. Okay. This is the same thing as derivative with respect to x of 1 over e to the x. Since we don't know a rule right now for dealing with that negative exponent, we're going to deal with this as a quotient, where our numerator is 1 and our denominator is e to the x. So the derivative of our numerator is 0 and the derivative of our denominator is e to the x. And we're going to have our quotient rule is going to tell us to take u prime times v minus v prime times u all over v squared. It's going to be 0 minus e to the x over e to the x quantity squared is a negative e to the x over e to the x times e to the x. And so we get a negative 1 over e to the x, which I'll write back in exponential form as a negative e to the negative x. All right, we'll learn another rule in just a little bit to help us with that. Now let's look at u is equal to e to the x minus 1, and v is equal to e to the x plus 1. So u prime will be equal to e to the x, and v prime will also be equal to e to the x. So we have u prime times v minus v prime times u all over v squared. I see a common factor of e to the x in the numerator. Now I'm going to make that e to the x plus 1 minus e to the x minus 1, that over e to the x plus 1 quantity squared, and e to the x times e to the x plus 1 minus e to the x plus 1 over e to the x plus 1 quantity squared. E to the x minus e to the x goes away, and this is e to the x times 2 over e to the x plus 1 quantity squared. So that's 2 e to the x over e to the x plus 1 quantity squared. Make it clear that the plus 1 is not in the exponent, that it's down beside that. All right, now let's extend the power rule so that n is any real number. We've only been dealing with positive whole numbers so far, or positive integers. Now we're going to extend it so that it's any real number, and it follows the same rule. It does not have to be a non-negative integer. So let's go ahead and use it with these powers here. That's going to give me 3/2 x to the 3/2 minus 1 is 3/2 x to the 3/2 minus 2/2 is 3/2 x to the 1/2. This is 2 times x to the 1.5 is 3/2. And that 2 is going to pass through. And we just figured out that derivative with respect to x of x to the 3/2 is 3/2 x to the 1/2. So this 2 and that 2 will cancel, and I'll be left with 3x to the 1/2. Now I'm going to write this as the derivative with respect to x of x to the negative second. That's going to be a negative 2 x to the negative 2 minus 1 is a negative 2 x to the negative third is a negative 2 over x to the third. Let's come back to this one for a second, and let's try and use the product rule instead. And see if we get the same thing. So u prime v minus, or plus, excuse me, v prime times u is going to be equal to 2x to the 1/2, and then plus 1 x to the 1/2 is going to be a 3x to the 1/2 power, which is the same thing as what I had up here. right? Let's use the quotient rule here. U is equal to 1 and V is equal to x squared. U prime is equal to 0 and V prime is equal to 2x. So we want U prime times V minus V prime times U all over V squared. It's going to be a negative 2x over x to the fourth. Is a negative 2 over x to the third. And I get the same answer both ways, whether I use the power rule or the quotient rule. Now let's go ahead. In this case, I definitely want to use the quotient rule, where U is equal to 3x to the 5 halves, V is equal to 2x squared plus 4, U prime is going to be equal to 15 halves, x to the subtract 2 halves from 5 halves, and I get 3 halves. V prime is equal to 4x. So I want U prime times V minus V prime times U all over V squared. So I'm going to factor out the 2 from here to help simplify these 15 halves. 15 halves x to the 3 halves times 2 x squared plus 2 minus 12x to the 1 plus 5 halves. I'll simplify that in a second. Over 2x squared plus 4 squared. That will cancel. This leaves me with 15x to the 3 halves times x squared plus 2 minus 12x to the 7 halves over 2x squared plus 4 quantity squared. Now I want to do some fancy factoring. And I see my greatest common factor here is a 3x to the 3 halves. It's going to leave me with a 5 times x squared plus 2 minus 4 x to the 2 halves is x over 2x squared plus 4 quantity squared. It's 3x to the 3 halves times 5x squared plus 10 minus 4x. Let's just go ahead and write that in descending order. Over 2x squared plus 4 quantity squared. And I think I'm satisfied with that. I don't think that there are factors of 50 that add to give me negative 4. So I've factored that completely. If I wanted to pull out the 2 squared from down here, I could do that, but really there's nothing that's going to give me a 0 in the denominator there. So I'm not really worried about that. All rules can appear in any given problem, and there's not only one way to solve most problems. So practice a lot and get used to good bookkeeping, meaning make charts like I'm doing here, declare your variables and your derivatives and be very careful with them. Use colors if that helps you, highlighters and so on. Too many colors gets distracting to me. And I just don't keep all those colors around all the time. It's nice to do this in a PDF here where I can change colors so easily, but that's typically not what I'm doing when I'm doing my homework. So let's look at a more advanced example here where my u is equal to 4x e to the x, and my v is equal to x squared plus 1, and I have u over v here. So u prime is going to be, there's actually going to be a first part and a second part here that I have the product rule. So derivative of the first part, leaving the second part alone, plus derivative of the second part, leaving the first part alone. v prime is going to be 2x. So u prime is going to be 4e to the x plus 4x e to the x. I think I'm going to leave it all out like that until we get done, and then I'll try and factor. So I want u prime times v minus v prime times u all over v squared, what y prime equals. So y prime is going to be equal to, let's factor out here. Looks like I have a 4x or a 4e to the x that can come out here. That leaves me with 1 plus x squared plus 1. I'll combine those in just a second. Minus, and this is an 8x squared, e to the x over here, for x squared plus 1 squared. So I have y prime is equal to, and between these two, I have a 4 e to the x that can come out. That leaves me with x squared plus 1 plus x cubed plus x minus 8 divided by 4 is 2. Leave those x squareds, so e to the x has come out over x squared plus 1 quantity squared. Y prime is 4e to the x times x cubed minus x squared plus x plus 1 over x squared plus 1 quantity squared. And don't think that that's going to be factorable. The only rational zeros there are going to be 1 and -1. And let's see, -1 minus 1 minus 1 plus 1, that's not going to work. And plus 1 minus 1 plus 1 plus 1, nope, that's not going to give me a 0. So that's fully factored there. All right. So let me scroll on down here. 4e to the x times x cubed minus x squared plus x plus 1 in the numerator, and x squared plus 1 quantity squared in the denominator is my final answer there. That's it for this video, and we will come back next time and talk about the chain rule, which happens with compositions of functions. Everything we've been doing right now has been with basic differentiation rules, and we're going to generalize those differentiation rules to help us with what happens when we have compositions of functions. So I'll see you next time for our next video on the chain rule.